Right? So in the normal sense of average, right, temperature is a measure of the average kinetic energy of the molecules in the object. And mostly we're going to be dealing with a gas, just because that's the simplest case. Um, but it's also true for solids, liquids, plasmas, what have you. Now, um, how does this relate to the average velocity of the atoms in an object? All right, so if here's Derek's block of aluminium from the video, and the temperature is 19 degrees C, um, aka it is 292 Kelvin, right? And someone, let's say this block of aluminium is just sitting in someone's hand. What are the average velocity of the molecules in this block?
Thermal energy? I don't know.
I mean, I'm looking for a number, right? So the atoms and molecules that make up this block, what's their average velocity?
Zero, right? Because they're not moving.
That's right. The whole block isn't moving, so on average, the molecules are also not moving. Right? That is, if we have here an atom of aluminum, and maybe it's wiggling back and forth because, after all, our idea of how a solid works is that there's actually some arrangement of atoms, and there are little springs, little tiny springs, connecting these atoms to each other. In chemistry, you might have called them bonds, but to physicists, they're springs. Um, and we know from looking at the springs, a couple chapters ago, and also in lab, that if you have something that's connected by springs and you just displace it a little bit and then let it go, it's going to wobble back and forth, right? So we're going to pull it this way, and then it's going to go back toward the center. It'll shoot past the center, its preferred position out here somewhere, and then it will go back to the center. So even though this thing is definitely moving, yeah, exactly, Jolene. This is Hooke's law for atoms. And the this idea of how solids work is actually called an Einstein solid. So this was one of Einstein's ideas that solids were basically just arrangements of atoms connected by springs. Yusuf, I like where your mind is headed. Um, at a molecular level, when we have an inelastic collision, so another way to say inelastic is plastic. So a plastic deformation, right, gets deformed, doesn't go back. What happens to the molecules? And that's a great question. They The impact could have given them enough energy to completely change their arrangement on a molecular level. If we have long organic molecules, like in plastics, then they could be twisted around each other. Um, there are also other things like spalling, which means that if you have an object and you hit it here, you get stuff flying off the back, so you actually lose material. All sorts of things. This is a rich field of study, and many people make their livings, studying what happens in inelastic collisions. But for our purposes today, uh, we are going to just focus on elastic behavior because it's easier and it's simpler. Um, um, but I don't want to minimize your question because in one sense the answer is lots of stuff could happen, and at the other end of that, depending on the material, the answer is we don't know exactly what happens. That's a field of active research. Uh, but for here, if we have non-deformed, things, this block, the atoms in the block are not stationary, but because the block itself is stationary, the atoms have to be stationary on average. Otherwise, the entire block would be moving. And the point of mentioning this is because just taking a regular average doesn't do the job we need it to do when we're talking about velocity, right? So if an object is stationary and you ask, oh, well, what's the average velocity of the atoms in this object? Well, it's going to be 0. What we do instead is we talk about the RMS velocity. Right? And RMS stands for root mean square. And what I'm about to write down is going to look very familiar if you are thinking about standard deviations. So when we take the root mean square, first we square the velocity. This way we always have a positive number, right? So velocity could be either positive or negative, but the square of velocity is always going to be positive. After we square it, then we take the average. And so we might average over all the atoms. And once we have taken that average, then we take the square root. All right. Does anyone recognize how this looks like a standard deviation formula? So one way of interpreting the standard deviation in statistics is the standard deviation is the RMS distance of your data points from your sample average. Yeah, there is an n-1 in the sample standard deviation, and that's for reasons that are beyond the scope of this discussion. But the general idea, right, is that in statistics, your data points could be greater than or less than the mean. So you square them, so the differences are always positive. Then you average them, then you square root them, so that everything is back down to the right size, more or less. So when we are talking about average velocities, we are actually going to mean RMS velocities when it comes to this chapter. So Jolene, the n-1 is because of an idea called degrees of freedom. And the why of it is buried several semesters deep into statistical study. But we can go down that rabbit hole privately if you like.
Dr. Wolf, just a quick one for the I under the sum symbol.
Mm-hmm.
Is that always 1 or what does it refer to?
Okay, so you mean this sigma notation here?
Yeah,
So
underneath it, there's an I, right?
yeah,
I equals one.
yeah.
Yeah.
So what this basically means is start with I equals 1 and keep adding up until you get to the nth one. And in the context of this discussion, that means start at the first atom, keep adding up the velocities until you get gotten through all the atoms. Right? So the I equals 1 and the n, that's just a way of keeping track of which atom you're on. All right. So something you've all probably seen in in chemistry is the ideal gas law, right? Raise your hand if you love the ideal gas law. So this is how a chemist usually thinks about it. This PV equals nRT. Uh, this is not how we're going to think about it. This right hand side is messy. Uh, we're going to deal with the much superior capital N KT. Right. Has anyone read the book and realized what the difference here is? The moles or something? Yeah. So chemists tend to think of things in terms of number of moles. Uh, Physicists are usually looking at smaller number of things, and so we think directly in number of particles. Yeah. So I say particles because they're not necessarily atoms. It could be molecules. So K here is Boltzmann's constant, which is a universal constant. In the units that we use, it's going to be 1.38 times 10 to the minus 23. Uh, the sharp-eyed among you may look at that and say, huh, 10 to the minus 23, is this related to Avogadro's number? Uh, and yeah, it is. So, Boltzmann's constant times Avogadro's number gives you the ideal gas constant. Just like in chemistry, we are always going to think about this temperature in kelvins. Unlike in chemistry, we only have one unit of pressure and volume that we're going to deal with. None of this millimeters of mercury BS. Our pressure is always going to be in pascals. And our volume is going to be in cubic meters. No, no atmospheres. Also, we don't we don't fool around with this Charles's law and Boyle's law and Dalton's law. No, none of that. We just go straight to the ideal gas law and we get what we need from it. All right. Questions or comments here? Has everyone seen the ideal gas law at least once before, or should we go over this? All right. We will we will talk about this in a little more depth. This is how I feel about chemistry. This may make me a bit of a snob. So the ideal gas law is an approximation, like many of the things we use in physics. It relates the pressure, volume, and temperature these are what we call state variables. So if you want to describe the state of a system, these are the things that you need to describe. And once you've specified the pressure, volume, temperature, and number of atoms in a system, you have in effect described it well enough that any other person doing physics is going to know what you're talking about. By state, I don't mean solid liquid. I mean exactly these things. So the not so in physics, when we're talking about solid or liquid, we will usually use phase. And state will refer to these descriptors. Yeah, chemistry is a hell of a drug. So those chemists, they're none too careful with their nomenclature. Jolene, what do you mean by standard versus not standard? Mm. No, we don't worry. We don't worry ourselves too much about that either. Yeah. I mean, physicists are the ones that design rocket engines, so we need to think about things in terms that work just as well in outer space as on the ground. let's do um, a typical calculation. This is a useful thing. So if we are in relatively standard conditions, right? We have our pressure is 100,000 pascals, right? This is approximately what it is in Las Vegas right now. The temperature is approximately 300 Kelvin. Again, approximately what it is outside right now. And we have, say, 1 mole of gas. All right. Any of you who thought that I was going to include decimal points on Avogadro's number have not been paying attention. uh, how much volume does 1 mole of gas um, take up under relatively normal conditions here? Well, we can solve for V. N kBT over P, and then we do a little plug and chug. So, well, STP is a little cold for me. I'm just going to say that. Right? What chemists call STP is 0 Celsius. Um, so my relatively normal is a little warmer. Yeah, this is always what Boltzmann constant is, as long as the units you are using are SI units. So um, meters, Kelvin, right? Kilograms. All right, so we have the 10 to the 23 and 10 to the minus 23 cancel. 6 times 1.38 is approximately 9. And then 9 times 300 is about 2,700. N is just a number of particles, so it's just a count. That's not 4. That's 3. Okay, so about 0.027 meters cubed. For those of you who absolutely must think about things in terms of oh yeah, Yusuf did the actual math instead of rounding in his head. Thank you, Yusuf. So this is, so for those of you who must absolutely think in liters, this is going to be 25 liters. So if you, took a chemistry class and they said, well, the volume is actually 23 liters. It's because they were using a slightly higher pressure and a slightly lower temperature. Um, Here in the physics department, we prefer to round aggressively. So 25 liters is close enough. So related question, what happens to the volume of this? How do we get to the moon by rounding? We made the computers do it. Uh, yeah, I mean, if you need an answer that has more than like two decimal points of accuracy, then yeah, you get a computer to do that for you. It's, you know. What happens if we take this gas that we have in blue over here and instead of I forgot what I was going to say. Oh, let's say you have this, you capture this gas and it's in a a hard glass container, so the volume of the container is not going to change, but then you heat it up, right? You submerge it in boiling water, maybe. So now it's temperature. So the new temperature is now 373. Right? The temperature of boiling water. So we get to use my favorite algebraic trick here. We get to divide an equation by another equation. So P1 V1 equals N1 KT1 divided by P2 V2 equals N2 KT2. So in this case, we're taking this glass container full of gas, submerging it in boiling water. We're not allowing gas to escape, so the ends cancel because they're the same. Since the container is rigid, the volume is not changing. And of course, K is just a constant, so that cancels. Any of you chemistry aficionados out there might realize that chemists give this relationship an entirely different name, but that seems like way too much work. This is just a result of the ideal gas law. Jolyn, why does the N cancel? Because if we're not letting gas in or out of the container, then the number of molecules in there is the same. All right. So by heating the gas up to boiling water temperature, you go from 100,000 pascals to 136,000 pascals. It's about a 30% increase in pressure. That's right, Abigail. It's going to be 11, 12, 13, 14. All right. So that's the ideal gas law. Uh, is that an example problem? Yeah, that was two example problems. Let's get smaller. Right? So we started this discussion by saying that the temperature is proportional to the average kinetic energy. So the average kinetic energy is 1/2 mv, right? Where this is actually the RMS. And the temperature, right? Considering what we just did with the ideal gas law, the temperature is PV over NK. So if we're dealing with a gas, these two are interchangeable. But we still have to deal with this proportionality symbol, and we want to um, change this proportionality to an equals. And in physics, we like to we use something we call the thermodynamic temperature, which is actually Boltzmann's constant times the temperature in Kelvin. And this has units of energy. So it turns out that Boltzmann's constant is the thing that lets us make this proportionality a firm equality. There is a little bit more touch-up work to do there. So as it turns out, we have 1/2 kT of energy per degree of freedom. This does, confusingly, this is not exactly the same thing that we mean in statistics. So this is one statement of the equipartition theorem, that all of the energy that a particle has gets split evenly between its degrees of freedom. But we need to talk for a moment about what those actually are. When we deal with the ideal gas law, there are some assumptions that go into the ideal gas law. Does anyone remember what they are? No attraction between particles. Yep. What else? Yep, so there is a temperature region where the ideal gas works well. It breaks down at very low and very high temperatures. Uh, but the other important ones here is that for the ideal gas law, we assume that they are monoatomic. Right, so the more atoms that make up a molecule, the less ideal it's going to be. And there are definitely engineers who spend their careers measuring how much the ideal gas law is wrong for various gases. And you can find a list of those coefficients online. Maybe not on Engineering Toolbox, but definitely on Wikipedia and other places. If you have a monoatomic particle, that is just a single atom, it is free to move in the x direction. It is free to move in the y direction. And because this is real space, it's also free to move in the z direction. Right, so 3 dimensions of movement means 3 degrees of freedom. There are 3 ways that it can move. A diatomic molecule, say like oxygen, has also 3 translational degrees of freedom. But there are other ways that the particles can move as well. They can oscillate toward and away from each other. They can rotate. Right? The whole molecule can rotate. So here, there are 5 degrees of freedom. And for more complicated arrangements of molecules, or arrangements of atoms rather, in general, there will be 3 translational degrees of freedom. Right? So in other words, they can move in the x, y, and z direction. And then there will be 3n minus 3 rotational degrees of freedom. Well, rotational or vibrational. In this class, we're really only going to deal with these first 2, and even mostly we're just going to deal with this first 1, because it gets complicated quick. But if we have a monoatomic particle, it's got 3 ways that it can move, then the number of degrees of freedom it has is 3. So the total kinetic energy that it's got is actually 3 halves, right? So 3 degrees of freedom, so 3 halves kT. And on the other side is still 1 half. If instead of a single particle, physicists love to study single particles one at a time, but if you have more than one particle, then we just add a factor of n in there. So if we have n particles, right, and this is how I usually think of the equipartition theorem for monoatomic, for atoms. Okay. We have questions or comments on this page. You can totally use the ideal gas law for diatomic particles. And for most diatomic gases, at reasonable temperatures and pressures, you'll be wrong by only like 1% or so. And you know how I feel about rounding. 1% is not worth worrying about. So, yeah, both in real life and for this class, you can totally use the ideal gas for diatomic particles. More than diatomic, you probably need a correction term to stay within a reasonable accuracy, but sometimes people don't do that. um, does that answer your question? All right, so two takeaways from this so far. The two takeaways we want. Oh, why is it 3/2? It is 3/2 because there are 3 degrees of freedom. So there's 1/2 kT energy per degree of freedom. And if you've got 3 degrees of freedom, then in total you have 3/2 NKT of energy. Uh, we are going to do chapter 14 after the break today. So the sharp-eyed among you may realize, like, hey, if, for example, oxygen has more degrees of freedom, like a diatomic oxygen has more degrees of freedom than argon does that mean that argon heats up faster when you give it energy? And yes, it does. This is the origin of the of specific heat, which is the next thing that we're going to talk about. Yes, for diatomics it would be 5/2. No, we're not gonna quiz today. The quizzes have had a generally negative reaction. Um, okay. Uh, after finishing all the grading for exam 2, the people that are doing the quizzes are not the people who need the extra credit. So we will have a quiz for 15 when we come back. There's just too much material to get through today. Okay. So we have this idea after examining the equipartition law that maybe not everything heats up at the same rate, right? Because some materials just have more places to stick heat energy, right? So I think of each degree of freedom is like a bucket, right? And when you get some heat energy, you can stick it in one of the buckets, and the temperature of the system is actually a measure of how full all of these buckets are. So it stands to reason that molecules with more buckets will heat up more slowly. And if you've taken chemistry, you've seen this next relationship. For reasons lost to time, it is typical to use a capital Q to denote heat. What is heat? Right? Think about the video we watched to start the lesson. Yeah, it's not hotness, it's not temperature itself, it is a transfer of energy. Heat is like work. Heat and work are both ways to move energy around. And in fact, we will examine that relationship more thoroughly in chapter 15. So the idea here is that if you apply an amount of heat, then you will cause a change in temperature. Why does it transfer? I mean, that is a $10,000 question. We're going to examine that more thoroughly in 15 as well, but in the simplest case, heat likes to move from hot to cold. So there is a downhill direction for heat, and it likes to move from hot things to cold things. Which, agrees with our everyday intuition. It's always nice when that happens. All right, so if you apply heat to an object, you cause a temperature change. If the object is more massive, it causes a smaller temperature change. That makes sense, right? If anyone has ever tried to cook in an oven before, you know that thinly sliced foods cook more quickly than thick slabs of food. And this is why. C is not the speed of light here, but that's a good guess. I know C is an overworked variable. We call this the specific heat. And this is our material constant for the day, for the day. This is our fudge factor that lets us say, hey, actually, not all materials heat up at the same rate, right? Like we were just talking about, like diatomic gases heat up at a slower rate than monoatomic gases, and when we move into liquids and solids, the differences are even more pronounced. There's an enormous amount of constants this time. Yes. You are not wrong. So the last couple of chapters in this class are more like what you'll have in 152, which is like a brief surface survey of a topic, grab a couple of equations, do a couple of problems, move on. Why do you have to search for it? Is Googling too hard? Back in my day, like you're not on your internet browser when you're doing these problems anyway. Don't pretend. Don't tell me you're not using the internet when you do a test anyway. I was born at night, but not last night. All right. So specific heat, you look it up on Engineering Toolbox or Wikipedia, or you just straight up Google what is the specific heat of aluminum. The specific heat of aluminum, by the way, is 0.897. So what this means is it takes 0.897 joules of heat energy to raise 1 gram of aluminum by 1 degree Celsius. I mean, for in-classroom exams, uh, for an in-classroom exam, me personally, I would always just include um, the constants on the question. I don't know why I blanked on that word for so long. Um, so water is among all. In fact, water it has the highest specific heat of all out of all common materials. So it takes an enormous amount of heat to heat up water. Right? In some ways, it's kind of remarkable that so common a material should have so uncommon a property. Uh, but I mean, if it didn't, soup wouldn't be delicious, right? All right. Why can't you do that in online classes? I mean, in online classes, I feel like it is incumbent upon everyone to use online resources. Um, and and realistically, like in the real world, like people don't memorize all these things. They look up everything they need as they need it. So I feel like it's definitely I feel like it's a more realistic experience. Nathaniel, you are on to something for Hot Pockets. And actually, we will uh, get to that in a moment, get part of it in a moment. Uh, but the real reason for Hot Pockets being cold is that there are hot spots and cold spots in your microwave. Heat, right? Energy is not distributed equally in the interior of your microwave. It's real weird. Okay. Related to this Q equals MC delta T stuff, it's going to be pretty common that we are going to be dealing with insulated uh, situations. So when things are insulated, what we mean is that if we add up all of the heat transfers, right? If we add up all of the heat transfers, some objects will be gaining heat energy, some will be losing heat energy, but if you add them all up, you get zero. And that's what we mean by insulation. So something. See, I don't actually know if you do this lab anymore, but uh, when I was teaching labs in person, we had this situation where we had a calorimeter of water. So there's water in this cup. And we had these metallic cylinders, which we submerged in boiling water. And then we pulled them out of the boiling water, put them in to the room temperature water, and measured how much the room temperature water heated up by. Used this as a way to solve for what the specific heat of the metal must be. So if we do something like this, we've got something like the heat, which is lost by the hot metal, is going to be plus the heat gained by that room temperature water should equal 0. We know the mass of the metal cylinder because we measured it ahead of time. We don't know what its specific heat is. And the temperature change that metal underwent, right? It started off at 100 degrees because we stuck it in boiling water. And it got cooled down to whatever temperature it was, initially. Or cool down to whatever it was finally. For the water, right, we know what mass of water is in the cup because we're the ones that put it there. We know what the specific heat of water is because we looked it up on Engineering Toolbox. And the change in temperature, right, it heats up to the same final temperature, and it started off at, say, like 23 degrees. Something like room temperature. Right, so from here it's only 2 steps of algebra to solve for the specific heat of the metal. So we solve for that. We get, some number out of that, and then we go on Engineering Toolbox and we see what metal has the closest specific heat to what we measured, and we try and guess what metal the cylinder is made out of. That was a fun lab. I enjoyed teaching that one. Well, there were people that burned themselves. I mean, boiling water is involved, and you will always have someone who thinks they can stick their finger in the boiling water to pluck out the metal directly. But other than that, the whole experiment takes maybe 25 minutes.
For the temperature, the initial temperatures, the 100 refers to when it was submerged in that hot water bath.
Yeah,
Okay.
so that's right. Submerge in a boiling water bath. Water boils at 100 degrees. Um, so if you leave it in there for a little bit, the metal is also going to be at 100 degrees. Does that make sense?
Yes, thank you.
Okay. The W here just stands for water. The other way this question could go is I could tell you what metal the thing was, and I could ask you to predict what the final temperature would be um, once it had all, cooled off.
Sometimes it's possible for the sign to reverse, right? as in for it to become positive if it warmed up instead of cooled down, if that makes sense.
Right. So like if this is cooling, then this parenthetical term is going to be negative, and if it's heated, it's going to be positive.
Yeah, thank you.
All right, so that is one effect of heat and temperature, right? If you add heat to an object, the temperature goes up. There are some other effects that happen when you start raising the temperature of an object, though. You probably haven't noticed this in everyday experience, but when you heat things up, they expand. Yes, this is why hot pockets have little holes along the side, because when that steam heats up, it's going to expand, and if there's no place for the steam to go, your hot pocket is going to explode. Um, if you want to see this in gory action, just stick a hot dog in the microwave for 5 minutes, or tomatoes. Yeah, tomatoes are also a really good one to make a mess with. Uh, wow, so many questions about exploding hot dogs. Why do egg yolks explode in the microwave? Same reason. They've got a membrane surrounding the protein-rich as the fatty yolk, and there's water in those fats. When the water expands, if the membrane doesn't give, it explodes. Is that why you should put a cover over the food to better insulate it? Yes. If you don't allow the hot steam to escape, it can continue cooking your food. Butter also works. That's really gross. Um, would this happen to human bodies? That is also really gross. But no, your body is full of holes. Uh, yeah, we start to talk about exploding things, and chat goes just explodes. Dead bodies in decomposition. I mean, yes, that is true. So there, even though your body in general has holes, there are cavities in your body that are not very well ventilated. Um, when bodies decompose, you get more gas, right? So a solid organic molecule composes into multiple gas molecules, and then yes, you get problems. Why is microwaving a pizza by itself has a different result than microwaving a glass of water? That has to do with conductivity, and we're going to cover that. But water is really good at distributing heat throughout its whole body, the whole body of the object, where pizza is not. Potatoes? That's a good question. That's a good question, Emily. That's a good question, Abigail. And yes, this is why coastal regions have milder climates, because the ocean absorbs an enormous amount of heat during the day and gives it back off at night. Okay. All right. So, yes, things can explode if they're heated up and there's no place for the expansion to go. Um, the ideal gas law talks about how gases will expand when they are heated. So we still need a law that deals with not with other things other than gases. So you may remember from chapter 6, we had things, we had elastic relations. So I may mean chapter 5. Yes. So, right, so this is where the y is Young's modulus. Right, we do a similar thing for shear. We do a similar thing for volume. Actually, I think this book uses K for the bulk modulus. So since this is such a convenient form, we're actually going to write down a relationship for thermal expansion in the same way. Yep, Y for Young's modulus, I think S for shear and K for bulk. K does so much duty. Uses B for bulk? Okay. So we would like to write down an equivalent relationship, right? So right, so this is how it's usually written down for linear expansion, and then for volume expansion. Right. So there are mathematical reasons why we can get away with writing down a linear relationship like this. So as long as we're not heating it up, too much, then the relationship is going to be approximately linear, and that's because, for the same reason that Hooke's law, we could write down as linear, because no matter what kind of relationship you actually have, if you zoom in and don't let yourself consider too far away from this point, then the relationship is going to be approximately linear anyway. So even if it has some weird behavior at very high or very low temperatures, right around normal temperatures, we can get a linear relationship. Let's say, what's that equation with the beta? That is volume expansion due to heating. Why is beta 3 times alpha? that is a longer question than we can answer at this level. Um, but the kind of hand wavy answer is that things expand in the x, y, and z direction um, at the same time, and so that's 3 dimensions, and that's why it's 3 times alpha. Um, the more exact explanation has to do with some calculus, and we're trying real hard to stay away from that in this class. I mean, me too. I think calculus is one of the most beautiful things humanity has ever invented. Um, it's just not for this class. Yeah, and you should definitely watch Walter Lewin on YouTube. Um, let's say you have some jungle gym equipment, and one of the things that you have is like this metal bar between two metal posts. Right? Maybe kids swing on this or something. Right? And it's steel everywhere. Assuming that these steel bars on the side are not going to bend, right? Say that the distance here is what? 1 meter. That'll make the math easier. So it's a 1 meter bar, and it was designed so that it fit exactly at 20 degrees Celsius. So if it fits exactly at 20 degrees Celsius, what is the pressure on the middle rod at 40 degrees Celsius? Well, we've got this linear expansion relationship. So we know that the thing is going to want to expand due to the increase in temperature. Right? The coefficient, that alpha, we're going to have to look it up. So for steel, I mean, it depends a little bit on what alloy of steel you are using, but on average, it's going to be somewhere right around 10 to 12. So let's call it 10 to make the math easy. So alpha for steel we're looking to calculate how much that steel bar wants to expand when it's heated up. Today's lecture should go up over the weekend. All right. So the change in length, the original length is 1, like 1 meter. The alpha for steel is 10 to the minus 5. And the per degree Celsius, and the change in temperature is 20 degrees Celsius. Right, so 10 to the minus 5 times 20 gives us, well, 20 times 10 to the minus 5, or 2 times 10 to the minus 4. Right, so 2/10 of a millimeter is how much the bar wants to expand.
The 10 to the negative 5, that's the alpha that we looked up.
Yep. And I
And
just
then,
went over to engineering toolbox.
okay. And then there was a 1 there, so if it was a different number, we would have multiplied that by, like, let's say it was 2 meters
Right.
wide. Okay.
Yeah.
Thank you.
Very frequently, though, at least in physics and engineering, we're only concerned with the fractional change. So this quantity here is called the strain. So the alpha is 10 times 10 to the minus 6. So 10 times 10 to the minus 6 is just 10 to the minus 5. So once we have the amount that bar wants to expand, well, now we know that there are steel bars on either side of it, so it can't expand. So we can use the Young's modulus relationship and see, well, how much pressure would it take to actually compress the steel bar by 2/10 of a millimeter. Right. So the Young's modulus for steel can vary a lot depending on the alloy. But I'm going to pick a cheap steel and say that it's maybe around 200. 200 gigapascals. So our Young's modulus is 200 times 10 to the 9. And the fractional change in length here is 2 times 10 to the minus 4. Right, remember our original length was 1, so it's 2 times 10 to the minus 4 over 1. Put these together, and we get, 4 times 10 to the 7. So this is the Young's modulus for steel. Again, look that up on Engineering Toolbox. Yeah, it's 200 gigapascals. So giga is billion, so 10 to the 9. So this is actually a pretty large number, right? So 20 degrees rise in temperature. ends up causing 40 atmospheres of pressure on this steel bar. All right. Questions or comments? So if it asks for height, would we use change in volume or L? I mean, L is like the Young's modulus one or the linear expansion one. That's for any expansion in one direction.
I just want to understand that second part. So the first part we measured when heating up that steel bar, how much it expands.
How much it wants to expand by.
Yeah, it's just like that other chapter of shear and bulk, and all that makes sense. And then the second part, we calculated the pressure for what?
The pressure it would take to keep that bar from expanding, right? Because our steel bar at the top is wedged between two other steel rods, so it actually can't expand. So even though it wants to expand when it heats up, it is prevented from expanding by two other steel bars. And so instead, there must be a considerable amount of pressure exerted to keep it from expanding. Right? So temperature wants it to expand, external pressure wants to squish it, and those two exactly cancel out.
Thank you so much. That makes a lot of sense.
Yeah, you're welcome. Yeah, you should definitely go over 5.3 again if you need to refresh on the elastic stuff. And the way we dealt with the elastic stuff is exactly how we deal with the expansion stuff now. We're not going to quiz today. There's too much material to get through. So we have covered most of Chapter 13 and parts of Chapter 14 at this point. I think it might be a good time to take a break. My clock says 10:06. Let's be back here at 10:15 after we've stretched our legs and gotten some water. All right, welcome back, folks. Had a couple private messages asking about exam 3. It is going to be next week. It is going to be 2 questions per chapter. You pick the 5 that you want to answer and do your best on those. The chapters are 11, 12, 13, 14. Okay. So far, we've talked about when you add heat to an object, so if you add heat, the temperature goes up. If the temperature goes up, the volume goes up. And the one thing that we haven't covered is phase changes. Yes, all of 13 and 14, and no extra credit if you do more than 5 questions. I just graded you on your best 5. All right, no more questions about the exam until we get through all our material. So the last thing that we want to talk about is phase changes. So in physics, what we refer to as phases are going to be solid, liquid, gas. This is a simplification. There are actually many different ways to arrange a solid, for example. So, I think my own research is on the different crystal arrangements of solids in metals. But at this level, we'll just say that solid, liquid, gas are the phases that a material can be in. So far, this does not differ from chemistry, and in fact, this is, if you've had chemistry, you know this part already. So let's take water as an example. So if you have very, very cold water, you have ice. Right? Say you start off at negative 20 degrees Celsius. If you want to start at minus 20 degrees Celsius and end at, say, 70 degree liquid water, because you want to make a latte, how much energy do you need to add to this ice to get your liquid hot water so that you can make your latte? So you definitely have to heat up the ice to 0 degrees. Once you have liquid water, you also have to heat up the liquid water to 70 degrees. And it's worth noting that the specific heat of ice is not the same as the specific heat of liquid water. In between, though, once you have ice at 0 degrees, it doesn't automatically become water. You need to give it an extra kick to change it from a solid ice to a liquid water. So yes, specific heat is phase dependent. The specific heat of ice is different than the specific heat of water, which is different from the specific heat of steam. And you need to give it an extra kick to make it change phases even once you've gotten it up to the melting point. Does it start sweating through at 0 degrees? Um, no. If you stop adding any energy to the ice at 0 degrees, it will remain 0 degree ice. So the specific heat of ice, like solid ice, is only about uh, is only about two. I better look it up. Yeah, it's two. So you want, if you want your 20 grams of water to make your espresso with, then you have to start with 20 grams of ice. The specific heat of ice is about 2 joules per gram degree, and you have to heat it up from negative 20 degrees to 0 degrees. Right, so this is our MC delta T from before the break. And once you've got liquid water, you also have to do an MC delta T, 20 grams, 4.18 joules per gram degree C, 70 degrees. And in the middle, that's where this new bit happens. And the energy it takes to move 1 gram of 0 degree ice to 1 gram of 0 degree water is called the latent heat of fusion. Right? So you may remember from chemistry that the heat of fusion is the energy difference between the solid and liquid phase. The heat of vaporization is the difference between the liquid and the gaseous phase. Right? For water, the extra energy you need is what? It's 334 joules per gram. So the to heat up the negative 20 degree ice up to 0 degrees, this takes 800 joules of energy. To heat the 0 degree liquid water up to 70 degrees takes 5,852 joules of energy. And to melt the 0 degree ice into 0 degree water takes 6,680 joules of energy. So in total, it's going to take 13,300 joules to start turning your ice into a latte. So this middle term is a mass times the latent heat per mass. Questions or comments here? How did you get 334? I looked it up on Engineering Toolbox. I mean, you could
So,
also memorize it if you felt like it, but I hate memorizing things.
sorry to interrupt. So for each Q, we've done MC delta T. Is that what, but the middle one does not have a delta T?
Right, because we're not actually changing the temperature. We're changing the phase. So on the left and the right, we are changing the temperature of the ice and the liquid water respectively, but in the middle term, we're just changing it from ice to water without changing the temperature.
And that would require, what's the L here?
The L is the latent heat.
Okay, thank you.
Yep. And so from right, so if we have solid, liquid, gas, from solid to liquid, we call that the heat of fusion. From liquid to gas, we call that the heat of vaporization. And from solid to gas, anyone remember what the phase change from solid to gas is?
Sublimation.
You got it. Sublimation. Right? It's some materials skip the liquid phase altogether. Can anyone? I was just gonna say, Megan, like dry ice, which is carbon dioxide. So carbon dioxide will go straight from a solid phase to a liquid phase, or sorry, solid phase to a gaseous phase, at normal pressures and temperatures. You have to compress it pretty hard to liquefy carbon dioxide. Okay. Any other questions on this slide? Okay. Uh, so that covers all of chapter 13 except 13.6. 13.6 is about humidity and evaporation, right? And there's equilibrium vapor pressures that exist um, above liquids. That's something that you'll deal with in chemistry, pretty thoroughly. So I feel safe in skipping it here. So let's finish up chapter 14. So we've already covered sections 14.1, 14.2, 14.3. So now we just have the back half of chapter 14. I mean, chemistry is just applied physics after all. Yusuf, are you reading my mind? I'm allowed to post this because I have a bachelor's in mathematics. And believe me, there are levels of snobbiness even within mathematics. Not all mathematicians are equally snobby. All right. So far, we have talked about the effects of heat when we move heat around, right? You move heat around, temperatures change, volumes change, sometimes phases change. Uh, we haven't yet talked about how we move heat around, but we're going to cover that now. There are three main ways of moving heat around. And you've probably heard all of these since, I don't know, middle school. We're going to be precise about what we mean by them here. Convection is also my favorite, but because of baking. Love me a convection oven. Not bake in, baking, like muffins. I could really go for a muffin. Yeah, now I'm hungry now. All right. Conduction is the main way that heat is passed through solids and liquids. Our idea goes something like this. Let's say we have a strip of material, and one end of the material is hot, and one end of the material is cold. These are relative terms. They don't actually have to be hot or cold, but there's a difference in temperature between the two sides. Our question is, at what rate is heat flowing from the hot side to the cold side? Because remember, heat flows from hot to cold, always. That's a law of thermodynamics. And we want to know how fast. Well, if this piece of material were thicker, right? If it were thicker, in this direction, had a larger cross-sectional area, it could pass more heat through it, just like a wider garden hose can shoot out more water. So we imagine that heat will flow more quickly if there's more area. We also know from experience touching hot stoves that heat will flow more quickly if there is a larger temperature difference between the hot and cold sides. And then lastly, we might imagine that if the distance between the hot and cold side is larger, that it might go slower, right? That you might have less heat overall passing through. So we'll toss in a distance there. And then lastly, because this is what physicists do, we'll throw in a fudge factor that we call thermal conductivity. Anyone want to guess what thermal conductivity depends on? Yeah, it's a material thing. Just because not all materials conduct heat at the same rate, So we're going to leave this job to the engineers, and they are going to give us a list of which materials conduct heat at which rates. And after they have done their important but considerably more boring jobs, we will be able to use their work to perform important calculations. No, engineers are not physicists. That's like saying mechanics design cars. No, there is a hierarchy here. I mean, engineers have to take physics, but so do you. Okay. And for anyone who's wondering why I'm using D for thickness here, it's because we already have a lowercase and a lowercase and an uppercase t in this equation. So t is right out. And also, Emma is correct. We are using K yet again for a completely different purpose. Yusuf, you heretic. All right. This is our idea for conduction. If there is a heat difference, through a solid, across a solid or liquid, heat will flow through the solid or liquid to get from the hot side to the cold side. Now we use like the language of fluids to talk about heat flowing or moving. On the microscopic side, right, what's actually happening, right? Because remember, these things are made of atoms, right? We have atoms vibrating very quickly on the hot side. They knock into atoms next to them, which cause them to vibrate, and we cause a chain of atomic vibrations all the way down. But as we go, some of the energy is lost at each step. So as we go to the left, the atoms are vibrating less and less quickly until we get to the cold side. So that's on the microscopic level. That's what's happening. But because there are just so many atoms in any bulk piece of material, we like to think of it in these terms rather than tracking what happens to each individual atom. We have questions or comments on conduction? The little t is time. That is an excellent question. Okay. Unfortunately, we are not going to be dealing with convection very deeply in this class. So convection is for fluids. But instead of having heat flow through the material, we just move the material. So, for example, if we have... Well, that's not the color I thought it was going to be. We have some fire. And we've got some air. Pretend that is air, guys. And then as we get closer to the fire, we get progressively hotter air. What's going to happen to the hot air near the fire? It's going to rise. It's going to move up. Why is it going to rise? It'll be less dense. Why will it be less dense? Because the volume increased. That's right. Because PV equals NKT. So temperature up means volume up. I was not going to say nRT. I would never. Whoops, crap. I accidentally messed up my screen. Okay. There we go. Why does the volume go up? So if the temperature goes up, then that means that this right-hand side of the equation is getting bigger. But for the right-hand side of the equation to get bigger, that means for the equation to continue to be true, the left-hand side also has to get bigger. Does that answer your question, Savannah? All right, got it. Cool. So the hot air will expand because it's hot. And because it's hot, it will be less dense because our density is mass per volume. So we haven't changed the amount of air, we've just changed the volume of the air. So density goes down. But from a couple of chapters ago, we know that the buoyant force on a material is equal to the density of the surrounding fluid times the volume times gravity. Right? So if there were no fire, the buoyant force on a layer of air would be just enough to keep it in position. It would neither rise nor fall. But when you heat it up and it expands, well, now the buoyant force, the amount of buoyant force doesn't change, but the volume, or sorry, the amount of buoyant force per, sorry, not the amount of buoyant force, but the pressure doesn't change, but because you've increased the volume, you've increased the left-hand side. So this air gets pushed up. All right, so that's the idea behind convection. Again, we're not going to deal with this at any bigger level than we just discussed. So the convection section is almost entirely qualitative rather than quantitative. However, we are going to deal explicitly with radiation. Thank you, Chad. I hope I got to my mute button in time. Okay. What is radiation? Lasers are one kind of radiation. Yep, we get another kind of radiation from unstable isotopes. Godzilla has radiation breath. Absolutely. Yep. So in chemistry, you learn about different kinds of radiation. Right? So we learn about alpha radiation, which is basically a helium nucleus emitted by an unstable isotope. There's beta radiation, which is either electrons or positrons emitted by nuclear processes. There's gamma radiation, which is just high energy photons. And all of these are correct, though from a physics perspective, these all fall under a specific category of nuclear radiation. Here, we're going to be concerned with a more general definition of radiation. So, electromagnetic radiation in other words, light. What in the world is a positron? A positron is a piece of antimatter which is the opposite of an electron. So from a physicist's point of view, all light is a kind of radiation. And all the way from radio waves to infrared light to visible light to ultraviolet light to X-rays and gamma rays. All of that, it's all photons, and we consider all of it to be radiation. The key thing here is that everything with a temperature um, is this physics 152? You will get more into light in physics 152 for sure. Um, everything with a temperature glows. Everything. The air, you, the sun, the ground, frogs, um, all of it. It all glows. The amount of energy that you emit by glowing is given by the Stefan-Boltzmann law. Q and T have their normal definitions here. So this little sigma here is called the Stefan-Boltzmann constant. This little epsilon here is called the emissivity. The A is the surface area. And T, of course, is the temperature. So the Stefan-Boltzmann constant, right? You just look it up. It has a specific value. It's always 5.67 times 10 to the what, negative 8? Negative 8. As long as you're using SI units, right? The units of this thing are a little weird. It's joules, meters squared. Oh, joules, whoops. Per meter squared. Seconds. Kelvin to the fourth power. The emissivity. Anyone want to guess? So the emissivity is a measure of how good an object is at glowing, right? There are definitely materials that just don't radiate, and though their emissivities are close to zero. And then there are materials that are perfectly radiating, and those have an emissivity of 1. And if you were guessing that this is a material constant, that material parameter that engineers get to figure out, you are absolutely correct. So, Jolyn, that has to do with fluorescence, which is a more complicated topic. Here, we're only concerned with light as a way to move energy, right? To change the temperature of things. So, your question is a good one. It's not what we're discussing here, but it is something. Well, no, we probably won't even discuss it in 152. But it is a very interesting topic. But this is why, for example, if you have an object and you just leave it out in an area, it's going to become the same temperature as its surroundings, even if there's no air. So um, you should note that we write this as if this is the amount of energy that an object is giving off, which it is, but we can also say this is the amount of energy that an object is receiving. So the net exchange of energy between an object and its surroundings via radiation, right? All these constants are the same. So the rate at which you're absorbing heat via radiation also depends on the Stefan-Boltzmann constant, also depends on the emissivity of the object, also depends on the surface area of the object. The temperature of the object represents how quickly it is giving off heat via radiation, and the temperature of the surroundings influences how quickly it is absorbing radiation from its surroundings. So since you notice that these are both raised to the fourth power, right, which means that if there's any significant temperature difference between the two of them, this can get significant fast. So things tend to become the temperature of their surroundings quite quickly. What about bioluminescence? Well, the prefix right there is going to tell you which class you should ask about that in. That's a chemical reaction. Frequency, it's actually a quantum chemical reaction, but that's a story for another day. Yes, we are definitely into the many formulas part of this series. So the first 8 chapters or so, 8, 9, 10 chapters, are very few formulas. Get used to being creative. And then the rest of the 151, 152 series is a whirlwind ride giving you a short look at many, many different topics. So emissivity is how good an object is at giving off radiation, but also how good it is at receiving radiation. All right. So that is the end of chapter 14. We have managed to cover all of 13 and 14 in just one class period, and we still have 15 minutes to go. Does anyone have any questions on this topic, related topics, life, the universe, everything? Yeah, we can totally do a problem from OpenStax. Which section do you want to pull it from? We are going to all of the sections in chapter 14 are fair game for the exam. So here's one from the book. Let's say you're on vacation and you're in a sauna. Now, a sauna is not a place that we typically think of as very bright. It's hot, yes, but there's not a lot of light in the visible spectrum. Right? But everything that has a temperature has a color and is transferring heat via radiation. So you walk into a sauna that is 50 degrees. Um, that's pretty warm, 110 degrees Fahrenheit or so. So calculate the rate of heat transfer to you, uh, given that your skin temperature is 37 degrees. The emissivity of skin is 0.98. That is, skin is really good at both absorbing and giving off radiation. And the surface area of your body is about 1.5 square meters. All right. Okay. So this is the Stefan Boltzmann law from the previous slide. The Stefan Boltzmann constant is 5.37 times 10 to the minus 8. Emissivity is quite high. Surface area of our bodies. And the difference in temperatures. Now the temperatures have to be in Kelvin. So our body temperature is 37 Celsius, which is 310 Kelvin. And the ambient temperature is 50 degrees, which is going to be 323 Kelvin. It's worth taking a look at what we've kind of implicitly defined the direction of this problem to be. Right, where this first term I've given a positive sign to, and that represents the energy that is leaving, right, going from the body to the system, to the surroundings. Whereas I've given a negative sign to this second term, which is the energy coming into the body from the surroundings. Alright, so all this stuff out front is 7.9 times 10 to the minus 8. And on the inside, we have 9.24 times 10 to the 9 minus 10.9 times 10 to the 9. Okay, so we take the difference here. We get a difference of, what, 1.6 times 10 to the 9? Alright, and then when we multiply these out, we're going to get a times 10 to the 1 because we have 10 to the 9 and 10 to the minus 8 here. And then 7.7 times 1.6 is about 12. Which is going to be just 120-ish, and that the units of that is in watts. How did it become 7.7? That is a really good question. I'm going to guess sloppy handwriting. All right. So you're getting a net 126 watts of energy um, on your the surface area of your body. What kind of issues, Jess? Why watts, not joules? Because it's heat per time. So energy over time is a power. Units of power are watts.
Just confirming the constant. It's 5.37, not 67, right?
Did I
My
write it
previous,
down wrong?
if I had a typo, but the previous one I have it is 5.67.
Um, it is 5.67. That's my typo. I'll be honest, I don't use the Stefan Boltzmann law well enough, or often enough to have it really memorized. Um, so in my head, it's 6. 6 times 10 to the 8. Okay. So for part B, what rate is the temperature of your body going to increase because of this? Well, so the heat per so here we have Q equals mc delta T, right? So the heat per time that is entering you versus the temperature per time that your body is changing. Right? We already know. Oh, we already know the heat per time is 126. The mass of your right there, our mass is given as 75 kilograms, and the specific heat, and your body is mostly water, so it's a pretty good approximation to just say that the specific heat of your body is the specific heat of water. And in joules per kilogram, that's 4,184. So something like you know, half a millidegree per second. Okay. The final is not on the 12th. The final is on December 10th. Exam 3 is next week on the 12th. All right. Yeah, none of these problems are bad. There are a lot more formulas in this section of the class than there were in the first part of the class. Uh, but we're only doing like surface level treatments of all of these things. So pretty much all the problems are going to be plug and chugs. What would the picture for this problem look like? It would look like this. They're talking about selling their soul, Jess. I wouldn't pay too much attention to them. The rate of return you get near final season is really low anyway. It's a buyer's market. There will be a curve in the end. Um, I don't know exactly what it's going to look like yet. I expect that the passing cutoff will be pretty close to 90 total points in the class. I mean, you don't need to skip anything. You should read it all because it's super interesting. But when I'm giving you a test, I'm only going to be giving you questions that you can do calculations for. So 90 points for somewhere right around 90 points will be a C minus grade. The final is going to be worth 70 points. So basically, 2 exams smushed together. Do I have any extra office hours this week? I haven't planned any, but if you need to chat with me, we can set up a time to chat. The final is supposed to be, what, 40%, right? Yeah, 3 exams are 60%, the final is 40%. So, yeah, so since the exams have been 35 points, 35-ish points, then the final should be about 70 points. Yep, that's the plan. So the final exam will have... The current plan is to have basically 1 question per chapter, and you pick 10 of them. How would you study for the final? Go back, look over any notes you have from problems you did as you were studying for the exams the first time. And if there's anything you seem like you couldn't reproduce now, then that's the section that you should study. We will also be having a review day before the final. So we're going to be having. We didn't do a toolbox update. There's at this point, like for this the second half of the class, doing a toolbox update is less important because there are just a lot of equations floating around, and they don't necessarily connect to each other in the same way they did at the beginning of the semester. Um,
Professor, could you make like a review test that we can all work on that's gonna be like similar to the final? I always find those like helpful.
I could the final is going to be it's literally going to be problems from the OpenStax book, just like the other exams. Um, yeah, it's going to be just the OpenStax problems with maybe some numbers changed around. So right out of the textbook. When we come back from Thanksgiving break on December 3rd, we're going to spend the entire 3 hours reviewing. So I am hoping that you will spend the Thanksgiving Day recess, and also after the third exam. So after our third exam next week, so then the 19th and 26th, you know, start going back over your old stuff. And if you have any questions about anything, December 3rd is when we're going to cover it.